radio call was VA3BJL, but I found out you could change your calls, pay $60, and you get a new call, and you keep it for life, okay? The reason I picked ZB was for Morse code, because most of the operators, you want to be very fast on Morse code, and you don't want to have to, you know, say anything lengthy. So the shorter your call, the better it is. So that's why it's ZB. Alan, how you doing?
Just wonderful.
Okay, we've got your
Here.
somewhere. There. Oh, you kept it. Oh, okay, good. Okay, now tonight's topic is antennas. And this is a fun topic. I tell you why, because you're not going to build your radio. It's, you know, you could build a radio. There are kits out there to build radios. But, you know, if you're going to build a really big transceiver, right, there's quite a bit of work, quite a few green boards, testing, and this sort of thing. But radio amateurs typically build their antennas. This is one thing that we build all the time, and it's fairly easy to do. And a typical radio amateur, of course, doesn't tune the antenna, or build it, or whatever until the winter. It seems that they always do this at the worst possible time of year that they work on their antennas. And I know I'm just as guilty as everybody else. I've worked on antennas in the cold weather, and it's not a nice thing to do. But anyway, there's all kinds of mechanical contraptions and, you know, things, how you get the pole up and how you put it in the ground, and all of that sort of thing is a lot of fun for us guys. Somebody else coming? Yeah. Very good. Here. I think I got them there, right? And, oh, sorry. Oh, yeah, Jack, sorry about that. Okay, so that's the nice thing about antennas, is that you get to you build them. Okay, tonight we have a bit of a problem because all of this is prepared for the screen, of course, but it's not working. So you need to bear with me. I'm going to try and do this by writing. Now, this was sent to all of you. Did you all get it at home? Oh, okay. Didn't look? Okay. So you have all of these notes at home. I've sent them to all students, okay? But anyway, we're going to go through it and talk about it and write some things on the board. So what is an antenna? And so it's a conductive device that converts radio frequency energy, RF as we call it, into electromagnetic waves. And it does the opposite. It converts electromagnetic waves into radio frequency energy. Okay. So this is the way it works. You heard about the transformer and how the transformer works, and power goes through the coils into the other coil. The process is called induction, right? Now, it's essentially the same for radio. A radio is essentially the same thing. You have your transmitter, which is putting out electromagnetic waves. But by the time they strike the other antenna, they are so very, very, very weak. But they are still there. And then the radio receiver takes those waves and amplifies them. The first thing you get in a radio receiver is an RF amplifier. It amplifies those waves and does a whole bunch of things to them, so that eventually you're going to be able to take the modulation off those waves and hear what the person is saying, okay? So an antenna is a conductive device converting radio frequency energy into electromagnetic waves. Okay, there's a whole bunch of things we need to know about antennas. Polarization is one, directivity and gain another, the length of the antenna, that's something very important, because on the test you're going to be asked about length. You're going to be calculating length of the antenna. Jason. Okay, radiation pattern. That's another very important thing about antenna. The bandwidth of an antenna. If it wasn't for bandwidth, we would all be in trouble. and the impedance of an antenna. Now you can go to work and Google picture of antenna, and you will find all kinds of pictures in Google of antennas, various antennas, how to build them, etc., etc. Okay, electromagnetic spectrum. This is really not on the test, but you should understand it. Over here we have, my writing is bad, gamma rays, X-rays, ultraviolet, I'll just put UV, then we have light, then we have infrared, micro, and then radio. These are all electromagnetic waves. So light is electromagnetic wave, okay? And radio is electromagnetic wave. Here, these waves have a long wavelength and lower frequency. As we go up, the wavelength gets shorter and the frequency gets higher as we get to gamma rays, okay? And the other thing that you should know is that the higher in frequency you go, the more energy there is in that electromagnetic wave. Paul. There you go, Paul. You're welcome. So that is the important thing. For example, around here, around this point, radio waves, microwaves, infrared, if you get too much of this, they will cook you. That's what your microwave oven does, right? It will actually cook your tissue. It will burn you. And as you go higher, the effects get worse. Gamma rays are the things that come off of, it's just light. It looks like light. It comes off exploding stars. It comes off nuclear bombs going off. And the gamma rays would actually just liquefy everything. They are so strong. Okay, they will just turn everything into mush. Yes? Wayne?
Not according to the Hulk.
Not according to the
Hulk?
The Hulk. Oh, okay. The Hulk.
Yeah, like, yeah,
That made him the Hulk. The gamma rays.
Right.
Yeah.
See?
There you go.
Well, I'm a science guy.
Anyway, so the important message to take away from here is that the shorter the frequency, the more energy in the wave, and therefore the more dangerous the wave. So for instance, 10 meters is more dangerous than 80 meters. 2 meters is more dangerous than HF frequencies, okay? So one of the reasons if you buy one of these that you should buy a phone as well is because you want to keep that antenna away from your head. Power is coming out of that antenna, okay? Yes?
Is that related to that whole cell phone radiation thing?
Yep, same thing. They have what are they, 800 hertz?
Yeah.
800 megahertz, excuse me, and you're holding it right here, and that power is going through your head. Now, if it was a lower frequency radio wave, of course, it's got a big, right, wavelength, but this is high frequency, so the wavelength is, and that's going through your head 1,000,000 times before it gets out the other end. Okay, so there are problems with radio waves, and one needs to understand this and be careful. Okay, that wasn't on the test, but there will be a section on safety on the test, and later on, and that's what you will need to know, things that you will need to know about safety. Polarization. Brent went through that last time, and went through the speed of electromagnetic waves, 300 million meters per second. Usually they ask you to convert it to kilometers, so it's 300,000 kilometers a second. Is that it? What is it?
298 3,687.
Yeah, it's not exactly 300 million kilometers a second.
It's like, will they test except just rounding it off?
They'll only give you the answer. You have to pick one of three. You know,
Okay.
yeah,
So it's like multiple choice.
yeah, multiple choice. They're all multiple choice questions. Okay, Brent also mentioned that a electromagnetic wave has a, I don't know if I can draw this. It has one field this way, and then another one is coming from the other side that way, and then one. I don't know if I can draw this correctly. This is hard to do without my. Anyway, it has an electrical and a magnetic field, and it's the electrical field that determines the polarization of the antenna. Brent went through this last time. The E field that determines the polarization of the antenna. So that's what you have to know. You have to know the E field and the H field, and the E field determines the polarization. And it's very simple. If the E field is horizontal, then the antenna is horizontally polarized. If it's vertical, then the antenna is vertically polarized. Now, it's not a problem for HF, as Brent mentioned, but it is for 2 meters. So you can't have this one, which is vertically polarized, and then put this one horizontally polarized. It won't work. It might work, but you get very little power. They both have to be vertical, okay, for UHF, VHF. But on HF, it doesn't make a darn bit of difference because of a thing called Faraday rotation. So it goes up into the ionosphere, and it's going to be all jumbled up anyway. So it doesn't make, on HF, polarization is not an important issue. Question? No? Okay. Okay, so next is directivity and gain. Okay. Well, gain is the ability of an antenna to convert the RF into a beam. See, and so what it's actually doing is it's stealing power from one direction to put it in another direction. That's what gain is. And it's not the same as electronic gain or electronic amplifier. It's not really doing that. Electronic amplifier is boosting the voltage, right? This isn't doing that. This is taking some of the power that might go that way and is pushing it this way into a beam. The greater the directivity, the greater the gain. Now, gain is measured in decibels, and you have to have something to compare it to. So there's 2 theoretical antennas that they compare it to. One is the isotropic radiator. Okay, the isotropic radiator, and the other one is the elementary Now these are theoretical antennas. They're not real, because real antennas have to take into consideration the ground. They have to take into consideration all the metal that surrounds them, your eaves trough, all of these sorts of conditions real antennas must face. These are theoretical antennas because we need something to compare to. Okay, now the isotropic radiator, look at that as a light bulb. A light bulb radiates in all directions, okay? An elementary dipole, you can look at that as a dipole, an antenna like this with the feed line, but it's theoretical. Now, when they compare them, what they do is they use these terms, dBi. If you go to buy an antenna, in one of the books you'll see this, dBi and dBd. This is dBd. Whoops. dBd. Is that a big D or small d? Let me see. dBd is a small d and a small I. dBi. Okay, these are the things that you'll see. And that's telling you gain. So you buy a beam antenna and it will say 18 decibels dBi. So it's being compared to an isotropic radiator. Or it'll say, 10 decibels dBd. You're comparing it to a dipole. Okay, so remember that gain is the antenna is turning it into a beam. So here, if you have this antenna here, which is like a light bulb, it's radiating in all directions, right? It's like a light bulb, it's going everywhere. That signal is going everywhere. North, south, east, west, up, down, etc. Well, what gain is telling you is that instead of doing that, it's pushing it like this. It's pushing it mainly in one direction. Okay, that's what gain is doing for you. The power is going in one direction. Okay. An amateur dipole, the kind that you would string up yourself, usually has 2.16 dBi gain. Okay, that's this standard amateur dipole has 2.16 dBi gain. I think you need to know that. So what are decibels? I don't want to get into what decibels are because it's kind of complicated. In the back of the book they have an explanation of decibels, and if you take the advanced course, you're really going to need to know decibels for the advanced course. If you're into any type of electronics at all, you'll need to know decibels. They're based on logarithms. But just remember, the decibels are a way of making power comparisons, and a doubling of power is 3 decibels. That's what you have to know. Doubling of power is 3 decibels. So the standard dipole antenna at 2.16 decibels, it's almost a doubling of power that you get out of a standard antenna. Okay, and we're going to show the pattern, the radiation pattern, a little further on of the standard dipole antenna. Okay, you've come across this before. Brent went through it the other night. And I really don't like I really don't like the way they do it. This is the way I prefer it. Okay, the wavelength is the speed of light over megahertz. Okay, well, why can we do it this way? Well, the speed of light is what? 300, 1, 2, 3, 4, 5, 6. Okay, the megahertz is whatever. Let's say it was 1, 2, 3, 4, 5, 6, right? Okay, well, why do you need all those zeros? Just take 300 over your frequency in megahertz and you've got it. So that's the simplest way to do it rather than converting it to anything else. So just put in here 300, and as long as you keep that in megahertz, right, then this is going to give you wavelength. Very simple. And this becomes the basis of the length formula. Okay. Okay, here we're saying, oh, are my pages mixed up? Okay, so we're talking about length now. Okay, the wavelength here is essentially the length of the antenna. So we have our dipole antenna, and the wavelength is the length of the antenna. The length has to be correct for the frequency that you're using to get the maximum power transfer. When that's the case, the antenna is said to be resonant. If this is cut for the right frequency, then you have a resonant antenna for that frequency. And although the antenna, like I could cut this for 20 meters, let's say, although the antenna is resonant for this one frequency, let's say it's resonant for 14.010 in the 20 meter band, yes, but we don't have to cut an antenna for every frequency that we need. There are ways of getting around this problem, okay? But the length is a critical thing for an antenna for the transfer of power. It has to be essentially resonant so that the power will be transferred and you'll be creating electromagnetic waves. Okay, with dipole antennas, they are usually a half wave. That means the distance from here to here is 1/2 wave. And this is where everybody gets screwed up, including myself, because there's 2 1/4 wave elements in a half wave antenna. So each one is a quarter. Okay? And it's a half wave. The whole thing together is a half wave. And you have to kind of remember that, because when you're doing calculations, are you calculating the full wave, the half wave, the quarter wave, you know? So you have to keep those things straight. Now the formula for if you're going above 30 megahertz, the formula is essentially that for the length of an antenna. Okay, it's the same formula I had before. Okay, this would be the full wave antenna. So if it's a half wave, it would be 150, etc., etc. Quarter wave, etc., etc. Now, I see that in the book they're still using feet and inches, and some of the questions that they're going to ask you apparently on the test are still going to be in feet. So unfortunately, the other formula is length is 94 over megahertz. Okay, so that's the one in feet and inches. You pretty well have to memorize these things, because if you don't, you're going to be asked on the test to calculate, you know, a length of an antenna for this frequency, and you pretty well need to know these things. Okay, so if we go to this is above 30 megahertz. That's UHF, VHF, etc. But below 30 megahertz, the formulas change. Okay, so they change in this way. See, it should be 300, but it's 286. It should be 298 or 980 whatever, but it's 936. Okay, and there's two reasons for that. There's on HF, what happens is the length to diameter ratio has an effect on the length of the antenna. Length to diameter affects the antenna. So you have to take that into consideration. That's why you get the number changes. Also, the end of the antenna, you have an insulator there, right? And the wire's going through the insulator and coming back. There's capacitance at the end of that antenna. And the capacitance has an effect on the length. So that's why the formula changes for antennas below 30 megahertz. Okay? So, memorize them. You absolutely need them. Okay, now, a question. Here's a question I took out of the question bank. A half-wave antenna is approximately 65 feet each side of center. So they're telling you what the quarter waves are, right? 65 feet here, 65 feet here. Okay. Its resonant frequency will be approximately what? So now you got to figure out the resonant frequency. Okay, so this is a half wave antenna. What's 65 and 65? 130 feet in total. Okay. So there's the formula, but this is for a full wave. What would be a half wave? What's the half of that? For 936? 468. Okay. So now we take...
Would it work if we just doubled the footage? Like if we took it and went 260?
Yeah, you could do it that way too. Do it from a... Sure. Yeah.
Lots of ways to get to the same place.
Yeah, you could do it
As long as you get...
as long as you get the right answer.
Yeah.
Right. So, but we did it with 130. So we take how do we do that? We take the 468. We take 468, and we divide it by megahertz, which we don't know. A little bit of algebra here, and that's equal to 130. Right? So then we just work that through, and what do you get? I hear it. Somebody's saying it. 3.6, yes. 3.6 megahertz. 3.6 megahertz. Does anybody know what band that's in? Now, if you wanted to figure out the band, right, you'd have to go back to the formula. Okay, can somebody do that? 300 divided by, because we can't use this anymore. We're trying to figure a wavelength, so we can do it this way.
83.
Sorry?
83.
83. So we're in the 80 meter band. Okay? And these kinds of questions are the things they're going to have on the test for you. Okay? Now, so that takes care of that. Now, the higher the frequency, the shorter the antenna. The lower the frequency, the longer the antenna. Now, as it turns out, this works also with mechanical vibrations. Mechanical and electromagnetic things sort of are very similar in many ways. There are mechanical oscillators, for instance. Sound is a mechanical vibration, right? It goes up to 3,000 hertz. After that, it's going to become electromagnetic. Okay, so here is a piece of wire, which we can assume is our antenna, and we're going to give it a mechanical vibration. Now, if I make this piece of wire shorter, is the frequency going to be faster or slower? Faster. 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 So the shorter the antenna, the higher the frequency. The longer the antenna, the lower the frequency. Now Brent did a neat thing. He measured, hey, I got a tape measure here. They can't use it. He measured a person himself and then figured out what would be the frequency of the person. Well, what frequency would resonate, because everything is resonating. That energy is in the air, and that energy wishes to couple to everything. But it only couples when it's the right length. Okay? You get the right length, it'll want to couple, even the human body. So I'm 166 centimeters, 1.66 meters. And if you put that in the formula, you would find out that my body is susceptible to 90 megahertz, which is the FM band, right? There's 90, So those waves are going to want to couple with my body, okay? And so I would stay away from FM antennas if it were me, okay, because they can cause some problems.
What about, so you would be 90 and above would affect you?
Yes.
So like 130 or 107, they would all affect you because you're their full wave spectrum.
Yeah, I was using half wave, yeah.
No, your body, I'm just same.
Yeah, it wants to couple with that power.
Okay.
And you
But
know,
anything lower, because the wave is larger than you,
yes,
it doesn't affect
it doesn't affect me as much, right? Now, there were some people, here's an interesting sidelight, some people had bad fillings, you know, we call them amalgam fillings, and they can be like a crystal, right? And then there's, I suppose, saliva and other things going on there. Anyway, these people were close to FM radio stations, right? And the tooth is acting as a diode. A diode is a detector. Guess what happens? They're hearing the FM radio through their teeth. Their body is the antenna. Okay? So, kind of scary. Okay. An antenna is resonant at 5 megahertz. And this is a typical kind of question. To make it useful in the 80 meter band, what would you have to do? Okay, 5 megahertz. Now, what's the 80 meter band?
3.6.
3.6, 3.5. Good. So, and it's 5. So, 5 megahertz.
We have to shorten it?
No,
Like
you have to lengthen it. Yeah. You can prove that to yourself, that you have to lengthen it. Yeah, they've got a whole bunch of stupid things here. One is lengthen it, center feed it with TV ribbon, shorten it, ground one in. Well, let's lengthen it. Because you could figure out 5 megahertz, you could figure out what the length would be or whatever and go from there.
I thought the shorter it is, the higher frequency it picks up.
It is the higher frequency. Yeah, the shorter is the higher the frequency, but the lower the waveband.
Oh.
See, because the waveband is kind of like the inverse, the wavelength. So 3.5 megahertz is 80 meters, you see. So if I went down, if I went to 2 or 1.8, it's 160 meters.
Yep.
You see, so that's how that's working. Okay, so we went through that part. Now the radiation pattern. The half-wave dipole. Whoa, where is my thing here? So this is our half-wave dipole. And we want to know what is it, what's the radiation pattern coming out of this? Because we said it's giving you almost a doubling of power in the real antenna. Okay, so if you look at the antenna, here's the antenna here. Let's say this is north, south, and we're looking at it from the top, right? What are we going to see from the top? We are going to see this. Okay, these are the lobes that are coming off the antenna. This is east, is that right? And west. Okay, so the major lobes are coming off of this antenna east-west. So you have a north-south antenna, so the gain is in this direction. Okay, so this is the pattern. This is the radiation pattern. Now, if you looked at it from the end, if you look at it from the end now, then how is that working? I think your lobes are more like this now from the end. Okay? From the top, you're seeing those top parts. When you're looking from the top, you're seeing that. But when you're looking from the side, you're seeing this. Okay? More like a donut with a hole in it, which we're going to have later on in about 25 minutes. Okay. So that's now every antenna has its own radiation pattern, and some of them have different lobes, and we'll get into that. For some reason, I want to keep this dipole antenna on there. So here you have here's the ground, and here you have your antenna, okay, your dipole. Let's say we're looking at it from the end, and there's a wave that comes off of it, which we talked about last time, a direct wave, or direct ray, and there's also one that hits the earth and bounces. And there's an angle here. Those angles are the same. Okay, so then this becomes your reflected ray. Okay, now the interesting thing is the higher the antenna, that's going to change the angle. This is called the angle of radiation. So if we went up here, if the antenna was higher, then the angle of radiation is going to be lower. Okay, so let me see if I can draw that. So we're going to come there like that, and it's going to go there like that. So you see it's, whoops, it's this angle is equal to that angle. It's a lower angle of radiation when the antenna is up higher. Now that's important. If you looked at it from the side again, it would be, instead of being out like this, right, the higher you put it up, it's going to be like that. It's going to be closer to the ground. That's probably an exact, it's right on the ground. It'd never be right on the ground, but it's going to be in this vicinity. Now that's a low angle of radiation. Now why do you want a low angle of radiation? What is that all about? Well, there's a good reason for that. Because with the low angle of radiation, you get greater distance. So here's we'll try and draw the Earth. Here is your antenna. Here is the ionosphere. Okay, and if that lobe is coming off where you get a really low angle, let's say, well, let's start first with your high angle. High angle, okay? It's going to bounce there. That's where it's going to bounce. And you know that this is the skip zone. Okay, but if we get that angle of radiation nice and low, so it's here. You see? Now, see how much farther I've got? With a low angle of radiation, I can talk farther. So you want to get the antenna as high as possible to get that low angle of radiation. Yes, that is a very important thing. And as I'm going to talk about a little later on, we talk about types of antennas. The vertical antenna does have its problems, but one advantage of the vertical antenna, low angle of radiation. So it's very good for DX communication with that low angle of radiation. Okay. Okay, now bandwidth is another thing. Bandwidth is a range of frequencies that the antenna will work on. Okay? You've probably heard that term before. So we measure that. We measure bandwidth in radio amateur work in terms of what's called SWR, standing wave ratio. Okay, and I'm going to explain standing wave ratio a little further on. The bandwidth is the frequency range over which SWR will be 2 to 1 or less. Oh, you don't have to know that now. I'm going to explain it later. So this is one of the factors that we can use that tell us that you could cut one antenna, but because the antenna will have a bandwidth, you don't have to cut an antenna for every frequency. It will work over a band of frequencies fairly well, as measured by SWR. Okay, one of the ways of increasing the bandwidth of an antenna is to make the radiating elements bigger. Okay, the bigger the radiating elements, the greater the bandwidth. Now, you remember somebody was complaining about those CDs? Those discs, okay. Well, what some people do, you take the disc, right? But you have to cut the holes in exactly the same spot. Okay, you cut them, holes, whatever you want. And you make a whole series of these, and you put the wires through them. See? And the wires are going through them, and then you bring them here, you bring them all together here. Here's your insulator, and you make your antenna like that, your dipole antenna like that. Well, you will increase the bandwidth of your antenna because you've got more wires. The problem is it becomes heavier, and you've got probably a potential problem with wind, and what's going to keep this in place. It's going to jiggle all over the place. So most amateurs don't do it, but if it was critical that you needed that bandwidth, you could. That's one way of doing it. There is a question on the question bank that asks that, like, what it will increase the bandwidth of an antenna. Well, is the diameter of the elements that you're using. Okay, so we got to look at these bands. The 80-meter band, for instance, and the 20-meter band, because they're different. 80 meters is one of the biggest bands we have. It goes from 3.5 to 4 megahertz, and the 20-meter band goes from 14 to 14.35 megahertz. So here you have the band is 800 kilohertz wide, and here it's 350 kilohertz wide. Okay, so if you cut an antenna for the center of this band, whatever that is, the bandwidth, it'll work through your radio will work on the whole band. Okay, no problem. It'll give you a 2-to-1, no problem. But this one is too darn big to work. So what people usually do with the 80-meter band is they cut the antenna for a frequency close to a frequency that they want. So if you're a CW operator, you're cutting it close to this, 3.5. If you're a sideband operator, you're cutting it further up. Okay, so that's one of the ways of doing it. Okay. Yeah, because the dipole antenna typically has 300 kilohertz. So you see 300 kilohertz of bandwidth. It's almost covering the whole band. 300 kilohertz is not cutting it here. And another way to get around this nowadays, this is why people don't worry about bandwidth anymore, because we have great antenna tuners, and they will tune almost anything to almost any frequency. That doesn't mean that all that power is going out, because the power is going to be going, you're going to get more radiated power the closer you are to a resonant antenna, right? The closer it is to resonance, that's where the power is going to be. The farther you go away from resonance, your radio will tune it, but you may not get all the power out of it. Okay. What the antenna does, what the antenna tuner does, is it puts in inductance and capacitance. It throws that in there, and it's actually a little computer that does it. You hit the button. I hope to do it one day, show you here. You hit the button and it goes click, 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 and boom, you're tuned. Like not even a second. It'll tune doesn't really tune the antenna, it matches the antenna, but we call them antenna tuners. Okay, so if it's not resonant, even though the antenna tuner is making it work, it's showing you that it's matching. Okay, if the antenna is not that good, then you're not going to get an effective radiated power. Okay, impedance of an antenna. So you need to remember, what is impedance? Can anybody tell me what's impedance?
The resistance?
And two things together. Impedance is you're getting close, is a mixture of resistance and reactance. That's right. Because AC, which what we're putting through there is very similar to AC, so you're getting reactance in the antenna, and you're getting resistance from the wire. So you're having an impedance in the antenna. And you know, if you tap the antenna at different places, you will get different impedances. So what you want to know is the voltage and current distribution in a dipole antenna. You need to know that. Okay, so we'll draw it out here somehow. So this is supposed to be a squiggly line, and that squiggly line tells you that it's like an AC source. And here is the current. This is the current, and this is the voltage. So there's your voltage. This is max. This is your voltage min. Okay, and this is your I current max and your current min. Okay, so this tells you at the center you have maximum current, at the ends you have minimum voltage, or maximum voltage, minimum current. So which part of the antenna is safer to touch? The middle, yes, because you got high voltage here. That's why you have to keep the ends of your antenna away from people or dogs or pets or anything that can touch the end, because that's where they're going to get burnt. And what did the radio amateur say when he touched the end of his antenna? Megahertz. That's a sad joke.
Especially AM antennas.
Especially AM antenna.
Remember that?
Yeah, right. Okay, so now, so we have the high voltage at the end. It's dangerous. We have the high current in the middle. Okay, so if you're going to feed the antenna, you're going to put your feed line on the antenna. You're going to have high impedance here, and you're going to have low impedance here. So that's why most of the time we put the feed line in the center, because that's where the impedance is going to be low. But you can put it, you could put 400, 600 ohm, line here to feed it at the end. Yeah. It's saying, yeah, so if you're using the end of the antenna, you could use 300 ohm twin lead, but you would then have to have some balun to match the impedance to your transmitter, which is 50 ohms. If you feed it here, then it's going to be, there's another question, most dipole antennas, it's about 75 ohms here. That's a question they may ask you. It's 75 ohms, but it's not too much of a mismatch if you put 50 ohm cable on it. It's not a problem. They do make some 75 ohm cable as well that some people would use. Okay, we're going to get into types of antennas next. Any questions so far? I have to struggle here without my without the TV showing you all these nice diagrams, and I can run through it real quick. Okay, types of antennas. The dipole, we've already talked about that. This is what most people have in their backyard, or some version of it. Inverted V antenna, the trap dipole antenna, the folded dipole antenna. So all these antennas basically start from the dipole. The long wire antenna, the vertical antenna, the Yagi or beam antenna, and the dummy load. Those are all the types of antennas, and we'll go through each one with a brief description. Okay. Here's a question for you. At the ends of the suspended wire, at the ends of an antenna, wire insulators are used. These act to increase the effective length of the antenna, limit the electrical length of the antenna, allow the antenna to be more easily held vertically, prevent any loss of radio waves by the antenna. So what are the insulators for?
Loss.
Prevent loss? One would think so. And you know, this is how they write these questions. Their questions are very tricky. Although that is true, to prevent loss is true because it was laying on the ground, the real answer is limit the electrical length of the antenna. That's what so your insulator is where you control the length of the antenna. That's what it's there for.
It doesn't change if it comes in contact with a different metal?
No, not necessarily. So you got your insulator, and it's got a hole in it, and you put the wire through, right? And then what you do is you make the antenna longer, and you take that extra wire and you wrap it around here, right? So you have defined the end of the antenna here. You're defining it there with that one when you tie that around that insulator, okay? So if it's not the right length, if you need more length, then you undo that and now it's over here, you see? Or if you need to go the other way, now it's over here, you see? So the insulator defines the electrical length of the antenna. I know it's really an unfair question because in the way I answered it was it prevents loss, or which it does as well. But some of these questions is like, what is the most important answer? And I guess that's the way they did it there. A 40 meter antenna half wave 7 megahertz can be used on another band without tuning. What band is this? 40 meter antenna. What was that? That was 80 meter, right? So the 40 meter antenna can be used on another band. What band do you think it can be used on? Now this gets a little tricky mathematically, but just take a guess. 10 meter band, 15 meter band, 20 meter band, 80 meter band. So 40 meter antenna can be used on what other band? Any ideas?
20?
You would think it would be 20. You know, that seems logical. It actually happens to be 15. The 15 meter band, or 21 megahertz. And in the notes that I have for you, that I've sent these to everyone, there's an explanation of why this works. So if you want to know the mathematics, it's there in the notes. But most people just memorize that your 40 meter antenna will work in the 15 meter band. And the reason for it is it has two 33-foot sections, the 40 meter antenna, and they act as 3 half waves, 3 half wavelengths on 15 meters. That's all there is to that. Okay, so if you have limited area, and you want your antenna to work, one way you could make it work is you could take these ends and you could bend them around, right? Most people do that. They just bend the ends to fit their property. It's going to give a funny radiation pattern, but hey, you're going to get it in your property, which is the most important thing. The other thing you could do is you just put a coil here. Just take the antenna and coil it up. Now you've got to put these two coils in the same location, and they've got to be the same length, right? So you make coils and put them in. And they call them loading coils. There's no capacitor or anything in there. It's just extra length of the antenna. And you'll see this in verticals sometime. That vertical that Brent brought, it had a little wee coil in there. And so the coil means that it doesn't have to be this long, it could be shorter. Okay, so that's exactly what the loading coil does. Okay, the inverted V antenna, well, this is simple. The inverted V antenna is basically the dipole here. We're assuming that you have a support here, right? You have to have a support to hold that up. You have a support here and a support there, right? To hold the whole thing up. Well, the inverted V is you have one support and this is, you're going to have something that stands off here and puts an insulator here, and then you're going to bring your antenna down like that. You're going to have a post here and a post there, and you're going to take your feed here and you're going to bring that into the house. This should be about 120 degrees, 120 degrees. But this is where it's dangerous with an inverted V. Inverted V is a nice antenna, will give you a nice radiation pattern, etc., etc., and will bring the impedance into closer to 50 ohms. But the problem is that you've got an insulator here and tie down rope, and the problem is that people can touch it, and we don't want them to touch it while they're transmitting. So while you're transmitting, so make sure that this is high enough where you terminate it. Make sure it's high enough off the ground. I used 16-foot 4x4s and got them in the ground, and had to use a ladder to get up there so that nobody could grab the end of the antenna. The trap dipole is another form of antenna, and people are not tending to use these. It's just, I'm going through all this stuff because this could be asked in the question bank. Trap dipoles are multi-band antennas, and what they do is they put an actual parallel tuned circuit in the antenna. We got a few minutes to go. So yeah, so maybe we're close enough now that we should take the break. I see some yawning here, so I think you need some refreshment to spark you up. Okay. You see you after the break. Don't forget, grab a donut. Get them fast because there are more than 12 people here now.